All right, so we're going to do number 34. Sum from n equals 1 to infinity of 1 plus 1 over n squared e to the negative n. So first, we're just going to do some thinking out loud on the side here. So one thing I would think is, so the e to the n is probably going to be more significant than this n squared. So I probably want to compare to e to the negative n, which is 1 over e to the n, so that's geometric with r equals 1 over e is less than 1. So this is just my strategy that I'm thinking about using. Then I'm going to say, well, how would these two things compare? How would 1 plus 1 over n squared e to the negative n compare to just e to the negative n? How would they compare? Well, I'm taking each of the terms and I'm multiplying it by a positive number that is greater than 1. So this is always, even as n approaches infinity, I'm always multiplying by a positive number that's greater than 1. So this e to the negative n is always greater than e to the negative n. Now, I also know that e to the negative n is geometric with r less than 1, so it converges. So this converges. So the situation I have is that my series in question is greater than a convergent series. So that's one of the situations that does not work for just the straight comparison test. So the comparison test fails, in the sense that it gives us no information, no conclusion, because in order for the comparison test to work with a convergent series, I need my series to be less than a convergent series. This series is greater than a convergent series, tells me nothing. All right, so that tells me I should use limit comparison. So we're going to use limit comparison. And but I'm still going to use the comparison series that I thought about. So I'm still going to compare it to e to the negative n. But my thought process here tells me I need to use limit comparison for this. All right, so how's that going to work? Well, I need to look at a lot of times they'll write this in their justifications in the AP exam. It's not a bad thing to do. Let a sub n equal e to the negative n, and b sub n equal 1 plus 1 over n squared e to the negative n. So that just gives you a handle, a label to write, which sequence is which. And then I can say that the limit as n approaches infinity of a sub n over b sub n equals the limit as n approaches infinity. So what will that be? The a sub n is e to the negative n. And for my denominator, I have 1 plus 1 over n squared. 1 plus 1 over n squared times e to the negative n. And then what's nice is that in this ratio, now the e to the negative n's just cancel out. So I have limit as n approaches infinity of canceling the e to the negative n's, 1 over 1 plus 1 over n squared. Now, I can probably justify just going from right here and saying, okay, the 1 over n is going to approach 0, 1 squared is 1, it's 1 over 1, the limit is 1. I can just say that. A nice additional step, but probably not necessarily, is to say this is equal to 1 over, so what I'm going to do is just move the limit inside. And of course, there's, justifications can be rabbit holes. The fact that I can move it inside is because all of these functions like 1 over x and 1 plus x and 1 and the x squared, they're all continuous functions. So the limit can move inside those continuous functions. And then I could say that that's 1 over 1 plus 0 squared, and it's 1. But I think it would probably be fine to say 1 right there. Now, this ratio is not always going to be 1. All right. Sometimes it's going to be 4. It could be 7. It could be 800 billion, as long as it's not infinity, or negative 1, or 0. If that limit turns out to be 0, then I cannot use the limit comparison test. All right, so, but I got 1, and I'm going to note that that is, in fact, a positive finite real number. It could be, it could be pi. It could be anything, as long as it's finite and positive. So then I'm going to say, now, in order to complete my justification, I need to state what my comparison series is and that it converges. So I'm going to say sum n equals 1 to infinity of e to the negative n. And I think, I did this type of analysis here, but you probably would be fine to say that this converges because it is geometric with r equals 1 over e. I think we could take that as obvious from this expression. It's a geometric series with r equals 1 over e. But I do have to say, even though it's also obvious, I have to say what's important about that is that the absolute value of 1 over e is less than 1. So I'm showing that I know that, if I had, negative e, that would still be less than 1, but it would not converge. So I need to have my absolute value there. So I'm stating why that converges. And then I state my conclusion, sum n equals 1 to infinity of 1 plus 1 over n squared. Yeah. It's got to. E to the negative n converges by limit comparison test. All right. So the crucial things here are, I think it's not crucial, but it's very helpful to state what the a sub n and b sub n are. But you do have to compute a limit. You have to, all the work that computes the limit. This over here is optional. This stuff is important. State that your comparison series converges and why. And then if this one converges, your other one converges, and vice versa. If this one diverges, this one diverges. All right. So, and then I say by limit comparison test, and that's how I complete that justification. I'm sure we'll have ample time to practice these in class. In the meantime, here's your chance to try it on your own. It is Stuart Kokoska. Yes, Stuart Kokoska. Page 690, number 9 through 39, the multiples of 3. I haven't been doing that much in this class. I wanted to spread these out. So obviously what I mean is 9, 12. You're doing number 9, 12, 15, 18, 21, etc. Multiples of 3 up to 39. And you're also doing number 49, 50, and 52, which are the interesting challenge problems. That is your assignment on the comparison test. There are 2 comparison tests. There's the comparison test, and there's the limit comparison test. The comparison test is nice because it's easy, because you don't have to do this limit. But it doesn't always work because you have to be less than a convergent or more than a divergent. So if you're more than a convergent, it doesn't work. So your first instinct should be, can you use the comparison test? The regular comparison test. Comparison test light. Can you use the comparison test? If you cannot, then you must use limit comparison. And now, of course, if the limit comparison test doesn't work, then we might have to look at something else. But we hope that the limit comparison test works. But we are going to learn more tricks. Anyway, there you go. That is, yeah, okay. Sure. Oh, sure. Yes, it is done. All right, great.